So, hi everyone, and good morning. So let's kickstart our last day of this workshop. Thank you for coming. So our first talk of today is by Carlos Herdeiro, that is going to talk about light ring theorems. So please, go ahead.
So good morning, everyone. It's really a pleasure to be here. Let me start by thanking the organizers for putting together this nice conference and apologizing for only being here in the last day. I couldn't come earlier due to other constraints, which I'm very sorry about. So my title today is Light Ring Theorems, and I should actually probably say light ring topological theorems, because there's many other results that I will not cover. And I would like to start with 3 statements and 3 questions. So the first statement is the black hole hypothesis, that there's a wide range of observational evidence for astrophysical dark compact objects, which are interpreted as black holes. The second statement is the Kerr hypothesis, that astrophysical black holes are well described by the Kerr black hole solution vacuum general relativity. And the third statement is that the Kerr black hole has light rings, and light rings have a close connection with strong gravity observables, such as the ring down and the black hole imaging. And that leads me to 3 questions. The first question is, do all theoretical black hole solutions have Kerr-like light rings? The second question is, can theoretical horizonless exotic compact objects, echoes for short, have Kerr-like light rings? And the third question is, if so, could such echoes be astrophysically viable? So my talk, well, the goal is to give some partial, certainly not complete, but hopefully informative answers to these 3 questions. And I would like to start by reminding you of something that you know, the Kerr light rings, which are circular photon orbits on the equatorial plane of the Kerr solution. So in this plot, you can see the Boyer-Lindquist radial coordinate for the light rings. So for the spin parameter 0, they both the co-rotating and counter-rotating are degenerate that are equals 3m. And then as you increase this spin parameter, the radial coordinate of the counter-rotating light ring increases, whereas the one of the co-rotating light ring decreases. And this, of course, has bearing on this D shape of the so-called shadow, the shadow edge actually, of a near extremal Kerr black hole when observed from the equatorial plane. Because light rings and their impact parameters determine some particular points along this contour. Given that the importance of light rings, one may ask, do all black holes have light rings in any given model, in any given theory? And those are to be defined as planar in some appropriate sense, bound photon orbits. Well, there's a generic statement, you can call it a theorem, stating that a stationary, axisymmetric, asymptotically flat black hole in D equals 4 with a non-extremal, topologically spherical killing horizon admits at least one standard light ring outside the horizon for each rotation sense. For these, no field equations are imposed. And I would like to emphasize already is that also no Z2 symmetry is required. So there might be no well-defined equatorial plane as a fixed plane of this Z2 symmetry, which is where the light rings of Kerr were. And in that respect, maybe as a curiosity, but certainly interesting from my point of view, is that there are, in fact, black holes that have no Z2 symmetry, even with a connected event horizon. If you go to non-connected event horizons, it's easier. So this is an example that occurs in Kaluza-Klein theory in 4 dimensions. It's a rotating, electrically charged and magnetically charged black hole, sometimes called the Rashid solution, or the Larsen solution. And what you can see here is the isometric embedding of the horizon in Euclidean 3 space. It's clearly non-Z2 symmetric. There's no north-south symmetry. These are some contour lines for different parameters. Nonetheless, the so-called shadow, this dark region that you can see here, observed not only from the equatorial plane, but at any given angle, still offers a Z2 symmetry, north-south, but the lensing doesn't. And the light rings exist in accordance to the theorem, despite the fact that there is no equatorial plane. Now, this light rings theorem exemplifies the field equation's independent statement. And it's topological and associates to light rings a topological charge, which was first introduced in this paper a few years ago with Pedro and also Emmanuel Ebert. So because it's kind of important for what I'm saying, I will spend a few minutes discussing the rationale. The central idea is that light rings are critical points of some given potentials. These are not exactly the usual potentials that one learns in the first course in general relativity. They don't depend on the conserved quantities, but are related to those. There's two of them. And so as an illustration, here's the r theta space in usual coordinates for Schwarzschild, this potential. And there's a saddle point there. That's where the light ring at r equals 3m sits. These potentials define on this two-dimensional space, which I can call the non-killing space, vector fields as their gradients. So there's going to be two, v plus minus. Then if you, on this two-dimensional space, choose a contour, any given contour, and you circulate this vector field along this contour, the winding of this vector field will define a topological charge. I'm calling W here. So this here, omega, capital omega, is the angle that the vector field makes with any arbitrary direction you may want to choose. Doesn't matter. And because it comes back to itself, it must be 2 pi times an integer, and that's the topological charge. So as a simple example, here's Schwarzschild once again. Here's one of the vector fields. Here, in this case, they only differ by a sign. You know that the light ring sits there at r equals 3m, so theta equals pi over 2. Of course, this is just because of the choice of the coordinates. And then you choose any contour. Could be this one. It doesn't need to be smooth, but it needs to enclose the light ring. And you see how if you circulate this, say, in one given direction, in this case, I'm going, say, counterclockwise, and one can look at how the vector field winds. And you can easily see, just following it with your finger, that it winds once clockwise. So because the winding opposes the circulation, this topological charge is -1. And this is true for whatever contour you choose that encloses the light ring. On the other hand, if you choose any contour that does not enclose the light ring, you can check that the topological charge is 0. But not all theoretically possible light rings in any arbitrary geometry have a topological charge equals -1. Standard light rings, by which I mean they are Kerr-like and they are saddle points of the potential, as we've seen for the Schwarzschild case, they indeed have topological charge -1. Exotic light rings that could be either minima or maxima of the potential, they turn out to have a topological charge +1. Moreover, it's also easy to show that this topological charge is additive. That is, if you choose a contour that encloses several light rings, then the total topological charge is going to be just the sum of the individual topological charges of the light rings that are within this contour. Okay, then to establish a theorem, what you need to do is to say that there is a black hole spacetime. And this is boundary conditions. So you say that there is a horizon boundary condition. You could choose asymptotic flatness, but you could choose something else. And then there's regularity and smoothness everywhere outside. In particular, there is an axis boundary condition because we are choosing that there is axisymmetry. then you have to take this contour to the limit where it encloses all of the spacetime outside the horizon. You look carefully at the topological charge, and you show it's -1. So this means that there must be at least one standard light ring. This is valid for each of the two potentials, meaning, loosely speaking, one in each of the two given directions. But this does not exclude that black holes could have more light rings. But if they do, they must come in pairs, with one standard one and one exotic one, as to keep the total topological charge to be -1. And I emphasize that for this result here, no field equations are ever used. It's a matter of boundary conditions. So to the question one that I've asked, do all theoretical black hole solutions have Kerr-like light rings? The partial answer is that under the stated conditions of the theorem, and they do, and possibly even more light rings, but they must come in pairs as stated. But of course, this can be circumvented by changing the boundary conditions. And a curious example of academic interest, but nonetheless we like these kind of things to see the limitations of our results, can be found in asymptotically Melvin universes. In fact, the theorem kind of guides you on how to possibly find black holes without light rings. You may say, well, it's kind of natural, a black hole should have light rings, but you could come up with an example where it doesn't. And let me illustrate this precisely with a Melvin example. So as I've just told you, the asymptotically flat Schwarzschild black hole has this topological charge -1. So you may think if one could immerse it in a background that brings with it a topological charge of +1, meaning it always has a light ring which is of exotic type, then such nonlinear superposition in principle has, well, W equals to 0, topological charge 0, which allows, but doesn't guarantee, that there could be no light rings. Well, it turns out that the Melvin universe of electrovacuum, a very well-known solution, non-asymptotically flat, it's a self-gravitating uniform magnetic field, brings a light ring always, and it has topological charge +1. And then the Schwarzschild black hole inside this Melvin universe has a total topological charge of 0. And this does not guarantee there are no light rings. There are situations in which there are two, but for sufficiently large magnetic fields as compared to the mass of the black hole, indeed, there are no light rings outside of the horizon. Now, since these light rings yield critical points in the light scattering problem, you may imagine that the absence of light rings may lead to curious features in the imaging. In fact, if you imagine setting an observer facing the black hole inside this Melvin universe, and if you illuminate the whole system by putting a kind of colorful light source, just for fun, then what the equatorial observer would see is something like this, that we've called a panoramic shadow. That's because, thinking about backwards ray tracing, any light ray that the observer sends along the equatorial plane, the black hole is there in any given direction, except the one exactly behind the observer, will end up falling into the black hole. Of course, normally this would only happen, say, normally I mean for Schwarzschild in asymptotically flat, for sufficiently small impact parameter, smaller than that of the light ring, but there is no light ring. This illustrates the impact on the imaging of light rings, which in this case is dramatic, a very academic case, as I've said. Now, in fact, the analysis of light rings and their non-planar generalizations that sometimes have been called fundamental photon orbits provides a simple, albeit non-precision, diagnosis of how non-Kerr, like the phenomenology of a given alternative model may be. Now, besides imaging, light rings are also associated. They play a role in gravitational wave observations for events where one can see the merger. Part of the signal is the ring down, and it turns out that the ring down also has a close connection to light rings, as initiated by this paper here. This can be seen in the iconal approximation. where it can be shown that for spherical black holes, the real part of the frequency is associated to the frequency of null geodesics traveling on the light ring, this omega c, and the imaginary part is associated to the Lyapunov exponent, this lambda, measuring the instability of the orbit. The connection for more generic black holes is more complicated and I would say still under discussion. Nonetheless, this connection between ring down and light rings was used to hypothesize that horizonless ultracompact echoes, where here ultracompact means having light rings similar to black holes, would vibrate similarly to black holes when perturbed, at least initially, although there would be some late time information, these echoes in the signal that would be general in the echo case, but not the black hole case, because of the absence of an absorbing event horizon. And overall, these connections between light rings and observables, the bright emission ring in imaging and shadows and the ring down have triggered an immense amount of work and interest in these ultra compact echoes. And the question raised is how much does the data really favor the black hole hypothesis against a more speculative exotic compact object hypothesis? In particular, can these black hole mimickers really, with similar light rings in particular, but no event horizon, be mistaken and be contenders to explain the data? So there are many studies of this echo hypothesis. And this also motivates our question number 2. So on general grounds, can theoretical horizonless exotic echoes have curl-like light rings? Well, as you probably are aware, I mean, these echoes have the appeal, some of these models at least, that they could solve the singularity problem. Perhaps some others could actually also connect to the dark matter issue, which is a real problem that has been around for 100 years. Many models of these echoes have been actually proposed throughout the years, not always with the same motivation, different motivations, not always to replace black holes. Some actually coexist with black holes, and they do not solve, say, the singularity problem. And I've listed here a bunch of examples. Sorry if I've missed your favorite one. There's many proposals, but ideally, we would like to make generic statements. So here's one attempt at a generic statement. Again, some time ago, and I've already quoted this paper when I mentioned the topological charge, together with Pedro and Emanuele, we got another theorem, which was actually the first one, that applies to ultracompact echoes that can form from smooth initial data on Minkowski spacetime from an incomplete gravitational collapse. So you can imagine there would be a mechanism for forming these things. Perhaps some unknown physics would kind of stop the collapse to form a black hole. Now, the theorem states that axisymmetric stationary solutions of the Einstein field equations formed from classical gravitational collapse of matter obeying the null energy condition that are everywhere smooth and ultracompact, that is, they have a light ring, must have at least 2 light rings, and one of them is stable. So the theorem actually applies a little bit more generically than GR, as I will explain. And the proof is, again, based on this topological charge. So the idea is exactly the same as before, but now instead of a horizon boundary condition, one has a regular origin boundary condition. And this actually changes the direction of this vector field on that end. And then this allows the topological charge, or implies the topological charge is actually 0 rather than a -1 as in the black hole case. So this result only depends on smoothness. There are no field equations that are assumed. Obviously, it applies to flat spacetime. And as a corollary, any ultracompact echo with the given symmetries that it's smoothly deformable into flat spacetime, if they have light rings, then they must have them in pairs, with one being an exotic, one being a standard, so that the total topological charge must remain 0. And one perspective on this is that you could convert it into a dynamical picture, which is important, because if you'd like to speak about something that could exist in nature, then you should have an idea of how it forms. So if you start with some dilute initial data close to Minkowski spacetime, it could be, say, a regular star. For our purpose, it's almost flat spacetime, meaning there are no light rings. So here the topological charge is 0, and then whatever happens in a very dynamical process is not so important as long as it's smooth. No topology changes are allowed, which are not describable by GR anyway. We then just assume that the final stage is, again, an equilibrium ultracompact object. It is axisymmetric, it's stationary, circularity is also an assumption here. Then the topological charge must be 0. You could alternatively think even, regardless of what happens here, so here it's certainly not stationary, and certainly in general it will not be axisymmetric, but you could even connect these two ends by an off-shelf sequence of stationary and axisymmetric spacetimes where the topological charge is defined all along, and the topological charge must remain 0. So the punchline is that any stationary, axisymmetric, circular, topologically trivial echo that forms from an incomplete gravitational collapse, which has a standard light ring, must have an exotic one as well. Well, it remains to decide on what's the character of this exotic one. Is it stable, fully stable, or fully unstable? Well, if you consider the null vector, or a null vector that's tangent to this exotic light ring, under the given assumptions for the metric, we can show in full generality that at the light ring, the Einstein tensor, contracted with this null vector twice, is the Laplacian in this non-killing space, this R theta space, in these coordinates I've been using, of the potential that determines the light rings. Well, this is not exactly the same potential as before, but it doesn't change the conclusion. So then, for the first time here, if you'd like to assume the Einstein field equations, a similar statement holds in terms of the energy momentum tensor. And then it follows that if the light ring is a local maximum of U, then the null energy condition is violated. And conversely, if one imposes the null energy condition, the exotic light ring must be fully stable. We could do something similar for modified gravity in terms of an effective energy momentum tensor, just putting to the right-hand side of the effective Einstein equations everything which is not the usual Einstein tensor, and then you could make a similar statement in terms of that effective energy momentum tensor. That's why the theorem could apply a bit more generically in those terms. So to question number 2, our partial answer is yes. So can theoretically horizonless exotic compact objects have curl-like light rings? Yes, but under the stated conditions of the theorem, necessarily there's this extra baggage. There's an extra light ring, which is stable under the assumption of the null energy condition. Of course, a theorem could be circumvented by violating one of the assumptions, for instance, non-trivial topology, example, wormholes, non-smoothness, ad hoc boundary conditions. I mean, there's a lot of studies that just kind of they connect to different spacetimes with some matching. Of course, you can ask, and perhaps you should, is there any plausible formation mechanism in those cases? And this leads me to question number 3. If there are echoes with curl-like light rings, so that they could imitate black holes, could such echoes be astrophysically viable? Now, I mean, this is becoming a more difficult discussion because, first of all, you must define what is viable. Here are some possible viability conditions to appear in a well-motivated and consistent physical model, even if it's an effective field theory like GR, at least, the initial value problem should be well-defined, things like that. Have a dynamical formation mechanism. If it's to appear, it should form. How does it form? And to be sufficiently stable. It doesn't need to be absolutely stable, but sufficiently stable to play a role in astrophysical processes, the ones you are interested in. Then there is a possible generic viability issue for these ultra-compact echoes with a stable light ring, which is that the stable light ring may lead to a trapping instability. This has been discussed by several authors. It's sort of intuitive. You have this potential, well, for null perturbations, they might pile up there and end up kind of destroying the spacetime. But one thing is to have this intuition, another thing is to prove. Especially because some arguments would say that this is not motivated by a single mode, it's a kind of a piling up, so it's nonlinear in a sense. And moreover, even if it is present, there's an issue about timescale. So if the timescale is too long, then it's harmless in practice. So that would mean that the instability is irrelevant. Now, it would be interesting to test it, and we've tried to do it. Searching for a good testing ground for this putative light ring instability turned out not to be so easy, because you have to find a model that's free of other instabilities, like perturbative instabilities. There are modes that you know are growing. For instance, if it's rotating, there could be ergo region instabilities associated to the negative norm states and so on. And moreover, it should be prone to doing fully nonlinear evolutions, which means that the theory must be under control and the objects themselves, especially because of this possibility that instability might be nonlinear. Well, one testing ground turned out to be these models of bosonic stars, which are these lumps of scalar or vector, typically complex, and with a master, possibly with self-interactions, but not necessarily. And they form these sort of lumps of self-gravitating field. They are starred. They can exist also in flat space-time, cue balls, well known for many years in scalar case. And they are very amenable also to evolutions, even more than, say, usual kind of fluid matter, because there's no sharp boundary. There's the kind of exponential decay of the fields. There are no shocks. And what we've done in this paper, we've identified a few models of bosonic stars that can become ultra-compact, that is, develop the light rings, and this happens in regions of the parameter space where no other known instabilities occur, like perturbative or ergo region. So we could use them as an arena for testing these things. And what we want to know is the instability real? Meaning, when the light rings appear, is there a transition in the dynamical behavior of the object? And what is the timescale associated to that? Of course, it would be desirable to have a generic mathematical argument, like we've done for the light rings theorems. But there's no clear way of doing it, honestly, at this moment. And in the absence of that, perhaps looking at examples is what we can do. Then we, just to let you know a couple of details, we used a couple of bosonic star models as arenas. So the first one are so-called spinning protostars. So this is kind of Lagrangian for the ones of you that are interested. It's a kind of complex vector with mass, minimally coupled to Einstein's gravity. This is a usual plot of the domain of solutions. They lie along this red solid line. This is a mass versus frequency diagram. These solutions always have a frequency because they are like stationary states in quantum mechanics. There's always a harmonic time dependence. And so solutions to the left of this point here are ultra-compact. They have a light ring. Solutions to the left of this point here, they have an ergo region. So the solutions here are solutions that are ultra-compact, but they do not have they didn't have any other known instabilities. And the second model within also this class of bosonic stars, but now it's a scalar model with self-interactions. It's the solitonic model. And again, this dashed black solid line, like there, is where is our arena, because they don't have either an ergo region, but they are ultra-compact, and no other known instabilities in perturbative theory are known. So these are the corresponding frequency ranges. And the second step to do here was to perform fully nonlinear evolutions of these stars in these intervals, setting these stars as initial data, doing also outside to benchmark, to compare the fate. And what was found in these evolutions is that there is indeed an instability. The stars start doing something. in the ultra-compact range and no instability outside. So there is a transition, and this is the point. For the scalar model, which are more compact, turned out that in these two testing grounds, the scalar stars are more compact. We observed collapse into a black hole. Whereas for the Proca model, one observed a migration, a shedding of angular momentum and mass, and the stars becoming less compact. So here is the time scale for the instability, which is of the order of a few thousand light crossing times, so certainly not very long from an astrophysical point of view. And as you can see, the time scale for the instability seems to go up as one approaches the dashed line here, which is the line separating the ultra-compact regime from the non-ultra-compact regime. One nice way to actually see this in the case where we have this migration is to look at something that we proposed. It's called an effective adiabatic potential, which allows defining a potential for null geodesics in which the critical points are the light rings, even in an evolving spacetime, as long as it's not evolving too fast, and even if it's not axisymmetric, as long as it doesn't deviate too much from axisymmetry. It's a kind of, by doing some averagings. And doing that, so what you see here is the evolution of the circumferential radius of the two light rings in the migration scenario for the Proca stars. And as the time evolves, they actually merge and disappear. There's a little movie here which I could show you. So this you can think of as being, the potential for null geodesics. So 1, 2, 3, 4, 5 is for 5 solutions, equilibrium solutions, these Proca stars, becoming less and less ultra-compact. As you can see, there's the potential well. So this is the stable light ring, that's the unstable. So in the evolving solutions, there's this effective adiabatic potential, which is this red solid line. It evolves quite, there's this strong oscillation. So there's an averaged quantity, averaged over the periods of the lapse, which is taken to represent, the physical variability of the stars. So this red dotted dashed line is this averaged over the lapse adiabatic effective potential. Well, what you can see is that it's kind of migrating. It's migrating very close to the equilibrium solutions and tending towards, this potential well becoming less deep, so shallower, and the two extrema to disappear. You don't see it very clearly here, but after about 8,000, indeed they disappear, the extrema. And this is what you see much better here in this circumferential radius. I would like to add that this instability is quite subtle. So we've been running further simulations for confirming the instability observed for bosonic stars. These have been more simulations with the Einstein toolkit, exploring different gauge conditions, evolution thorns, resolutions, initial perturbations. And the conclusions that we'll present soon is that with this infrastructure that we have, that we've used for over a decade, that we've learned to trust to evolve these sort of objects, the instability is there, but it's quite sensitive to gauge choices, less sensitive to other things. So with this further reassurance to question 3, our partial answer is the trapping instability associated to these stable light rings, at least in this family of models, seems to be real, and it needs not be too long-lived. This questions the viability of some of ultra-compact echoes. Of course, there's a big generalization here if you'd like to make this a general statement. At least ones that have a plausible formation mechanism. If you think about, how things form, stars and even black holes from the collapse of some initial data. Of course, you could invoke something else like quantum processes that there's not really control over, and then say that there are different things that happen, topology changes, whatever. and then this wouldn't apply. But of course, again, to emphasize the limitations, only two families of examples, and there's many important open questions here. To finalize my talk, I would like to say that looking at this topological chart, coming back a little bit to the title of my talk, and this with different boundary conditions has proved to be an informative technique. I've listed here an incomplete set of examples. So besides what I've told you, that this topological chart is -1 for black holes in asymptotically flat spacetime, also there are some partial results for different asymptotics. So it turns out to be the case for traversable wormholes. So traversable wormholes are always ultra-compact. And also some swirling universes, some kind of different academic, perhaps, boundary conditions. As I've said, the topological chart is 0 for asymptotically flat, smooth, horizonless compact objects. There's some families of solutions. I mentioned the Melvin universe. Now, the Melvin universe can be embedded in Einstein-Maxwell dilaton with a varying coupling. There's something interesting that happens when you vary this coupling. At the Kaluza-Klein value, the total topological charge for a black hole immersed in this universe varies from W equals to 0 to W equals -1. It's kind of a curious feature. It varies precisely at the Kaluza-Klein value, which is very interesting because the Melvin universe in Kaluza-Klein is just a twist of 5-dimensional flat space-time, then applying Kaluza-Klein reduction. Then there's some interesting relations with ergo regions. There's some generalizations to higher dimensional black holes. There's some generalizations to non-spherical horizons and multi-black holes, then with João, who's also here. Generalizations to models where photons do not propagate along null geodesics. And the technique also inspired other attempts, namely for time-like circular orbits, although here only for special orbits, and something called the topology of black hole thermodynamics that I've seen many papers about, but I don't really fully understand it, I must say. But with that, and I think I'm over my time, so I think I'll stop here. Thank you very much. Thank you.